So there will be many questions from me during the course of the lectures. Okay, so you must say something, some response. So we will start with a question which is apparently not connected with what we were supposed to talk, but we will see how it comes into the picture later on. Okay, so the question is, the first question that is what are all the linear maps from R to R? Are you able to hear me? What I asked?
Yes, sir.
What are all so we can proceed only if you give some response. Okay. You know, R is a vector space over itself, right? Isn't it? So what are the linear maps from R to R? Give me one linear map to start with, then we can try to find all the linear maps. Give me one linear map from R to R. I'm just asking for one linear map from R to R to start with.
Sir, identity map.
What is identity map?
I from R to R, I of x equal to x.
Identity map. What does it do? X is mapped to
X itself.
Right?
Yes.
This is of course a linear map on any vector space for that matter, in particular on R. Can you modify it a bit? Still get a linear map? Instead of saying x goes to x, x goes to, say, 2x, for example. Is that a linear map?
Yes, sir. Yes, sir.
Yes. So what is special about 2? Is there anything special about 2 here? Instead of 2, can you have something else?
2 not equal to 2 constant.
2, of course, is a constant. That's okay. 2 is a fixed number. Is there anything special about 2 that's needed here? Give me some other number that you can take.
Where is the constant എടുത്താലും ആകൂലേ?
So x goes to
some cx.
x goes to kx. What is k?
Constant.
Constant means what?
Not equal to 0.
Where? Number I, for example. Can you take k is equal to I?
Real number.
Real number.
K belongs to R.
K is any real number. Okay. So you still get a linear map, right? What is the value of k? If you call this map as t, let us say, t is the map, x going to kx. Right? So what is k? In terms of the map, can you tell me what k is? In terms of t? Is it t of something? Which real number is mapped to k by t? T of x is equal to kx, right? So what is k in terms of t? K is equal to what? T of? For what value of x do you get k on the right hand side?
It's equal to 1.
X equal to 1.
X equal to? K is equal to
It's 1.
t of 1, right? The real number 1 is mapped to k by this t, isn't it? So you know what the constant is in terms of t. So if you take any real number k, just multiplication by k gives you a linear map on R. What happens if k is 0?
The map is some zero map.
Huh? What happens when k is 0?
Zero mapping ആവില്ല sir.
So t is the 0 map, right? So you don't have to exclude that. 0 map is still linear map, isn't it? So what does this say now? If you know k, you know the map here, right? But what is k? K is t of 1. So if you know the value at 1, you know the value at every point. Why is this? If you have a linear map on a vector space, if you know the values of the linear map on all basis elements, then you know the map at any point, right? Value of the map at any point. Because any element of the vector space is a linear combination, unique linear combination of the basis elements, right? So a linear map is completely determined by its values on any basis. Now here, of course, we have R to R. So what is the dimension? What is the dimension of R over R?
1, sir.
1. So how many elements does a basis have? The dimension is 1. There is a basis containing only one element. So can you give an element which gives you a basis? 1. The number 1, for example, is a basis, right? Yes or no? Any element of R is a scalar times 1. X is x times 1. So 1 is a basis. In fact, any non-zero real number is a basis, isn't it? Is that correct? Any non-zero real number is a basis for R over R. Because if A is any non-zero real number, any x you can write as a multiple of a, right? X you can write as x over a times a. A is non-zero, so you can divide by a. So the coefficient is x over a. So any non-zero element forms a basis for R over R. That's why. So of course, the most convenient one is to take just one, the number a as one. That's what happens here. So if you know the value of, if you prescribe the value at 1, then it determines the linear map completely, right? So if you define t of 1 as k and t is linear, t of x has to be kx. Okay, so now what have we done? Of course, we have just said for any real number, any fixed real number k, t of x is equal to kx defines a linear map on R. What happens if I add something? Suppose I define t of x as kx plus L. Is this a linear map?
Linearity condition satisfy ചെയ്യില്ല.
What condition?
T of x plus y T of x plus T of x for all.
Hmm?
T of x
What
plus y.
does this give a linear map for some value of L? What is the image of 0 under a linear map? If t is linear, what is t of 0? No, forget this map. I'm asking, if t is a linear map, what is t of 0?
0.
0. So what about this map? T of x is equal to kx plus L. When will it be a linear map?
If L is equal to 0.
If and only if L equal to 0, right? If L is not 0, T of 0 is not 0, so it cannot be linear. And if L is 0, it is a linear map, as we have already seen. T of x equal to kx is a linear map. Okay? So this is T of x equal to kx plus L is just a translate of a linear map. So what is called an affine map. Okay? Affine. Anyway, so that's okay. So, but now we want to start the other way. We want to start with given t from R to R is linear. So what we have done above is to give an example or some examples of linear maps from R to R. I'm starting with an arbitrary linear map from R to R. So how does it look like? Can you say something? Can you write down the expression for t, how it should look like? Remember what we have said just a few minutes ago. Okay, 1 is a basis for R, and if you have a linear map and you know the value of the map at 1, then you know the value everywhere, right? So t of x is what? So you are now given the map T, okay? So in particular, for example, you know what T of 1 is. You are given this. So call it something. Call it K if you want. Or A, anything you want. Then what is T of x? x is x into 1. X is a scalar now, so you can write this as x into t of 1. So you have called t of 1 as x, so this is nothing but kx. What does this mean? What have you shown? If T is any linear map from R to R, then T of x is equal to Kx. So earlier you said for any K, T of x is equal to Kx defines a linear map on R. Now we are saying if T is any linear map on R, then it is of the form Tx is equal to Kx. Right? So you know you fix the value at 1, then you completely know what T is at any point. Okay? So what are all the linear maps now? You answered the first question now. What are all the linear maps from R to R? So linear maps from R to R are precisely of the form Tx equal to Kx. The K is in R. For each K, you get a real number. For each real number K, you get a linear map. If you want, you call it, okay, let us say, we can call this as T sub K, where T sub K of x is equal to Kx, where K is any real number. Okay, so every K in R defines a linear map from R to R by x going to Kx. And of course, conversely, for any real number K, x going to Kx gives you a linear map. And of course, if we have two different real numbers, K1 and K2, the linear maps are different. So this is a bijection with this notation. K going to Tk is a bijective map from R to linear maps from R to R. So you know all the linear maps from R to R. They are just multiplication by a fixed real number. Of course, you can also check. I'm not going to verify this now. So this is also a vector space isomorphism, linear isomorphism. You know, all linear maps on a vector space form a vector space themselves, right? So the vector space of all linear maps from R to R is isomorphic to R itself. Okay? This is almost a trivial thing. Now let's go one step ahead. What are all the linear maps from R to R2? Okay, so again, start with some example. Give me one linear map from R to R2. Start with any real number T. You want to end up with element of R2. So two coordinates, both of them in terms of T, functions of T. So give me one linear map.
T of x equal to x0.
0. So every t goes to 0, 0. That's okay. Give me something non-zero. See, if you have a linear map from R to R2, so what is going to be the image? When you have a linear map, the range of the linear map is a subspace, right? On this side, the codomain. So the image is going to be a subspace of R2. So if it is not 0, it's going to be of dimension 1, right? It's going to be a straight line. One-dimensional subspace of R2 are straight lines through the origin. So how do these straight lines through the origin look like in R2? What are the equations of straight lines through the origin? If you have a straight line in R2 passing through the origin, what is the equation of this?
X equal to Y.
X equal to y is 1, right? Not the one I have drawn here. But so how do you write that in the as a map? T going to, so you want both the coordinates to be the same, right? T going to t comma t, for example, is a linear map whose image, whose range is just the line y is equal to x. If you take a straight line through the origin, how does the equation look like in general? A general straight line passing through the origin is going to be of the form ax equal to by or something, right? Or ax plus by equal to 0, whatever, right? So you can look at maps like t going to at, comma bt, for example. Fix, because this is not ax equal to by, but is of the form. What are a and b? A and b are some fixed real numbers. Or what is the same, this you can write as t times a comma b. It's just scalar multiplication in R2, right? You multiply each coordinate by t. So what does this say now? Therefore, if you fix any a comma b in R2, that gives you a linear map from R to R2 defined by TAB of t is equal to t times a comma b, or what is the same? AT or TA if you want, TB. See, just like in the previous case, so you fix a point in the codomain, right? Fix a real number k, map x to kx. That's what we did earlier. The same way, fix a point in R2, multiply that by the scalar t. That's all. So again, so TAB, AB in R2, this is same as a vector space is equal to, in fact, when you write all linear maps from R to R2. So any linear map from R to R2 is got by multiplying a fixed vector in R2 by the scalar t. That's all. Okay? Obviously, this extends to Rn. So if A is T of A, let us say T of A is T times A, where A is in Rn. So we fix A in Rn, multiply that by the scalar t, you get a linear map from R to Rn. So linear maps from R to Rn are just all maps of the form TA defined like this, where A is in Rn. What is T times A? If A is A1, A2, An, TA is just scalar multiplication, multiply each coordinate by T, A1. Okay, so now let's look at the reverse direction. R to R2, that's what we are looking at. Now, what about R2 to R? What are all the linear maps from R2 to R? So as usual, let us start with one example and then see what happens. Of course, 0 is always there, okay? 0 map is always a linear map. So give me one linear map which is non-zero from R2 to R. So you are in R2, so x comma y is mapped to something. This something must be a real number. So you start with a pair of real numbers and you want to end up with a single real number. So what do?
Sir, projection map. XY maps to X. Projection maps. XY map to X.
Projection what? XY goes to?
X or Y.
Okay, X, right, fine. Or Y. XY goes to X. This is one linear map. XY goes to Y is another linear map. The projection on the x-axis, projection on the y-axis, fine. Anything else? What about this? XY going to X into Y. XY, product XY is again a real number. So we are in R, we have ended up in R. Is this linear? X comma Y going to the product XY. Is this linear?
Yes, sir. Yes.
Why yes?
Q0 maps to 0. When
Yes.
we choose X and Y 0, 0, then XY always 0.
Yes. That is enough for linearity?
Sorry, sir.
What happens, for example, if you multiply this by 2 on the left hand side? 2 times xy. What is 2 times xy? Is 2x comma 2y, right? You multiply each coordinate by 2. So what will be this image of this? Under this map, x comma y going to product xy, this is going to be 2x times 2y, okay, 4xy. So you will not get 2xy, but you will get 4xy, okay. So what is the conclusion? This map is not linear, right? Correct? Yes or no? This is t of this. So this is not equal to 2 of txy. Isn't it?
Yes, sir.
So this is not a linear map. But actually it is what is called bilinear. It's linear in x, linear in y, but not linear in x comma y. We will not worry about bilinear right now, but just mention. Linear in each coordinate, linear in x, linear in y. So if you fix y, this is linear in x. If you fix x, this is linear in y. Okay, anyway, so that's all right. But so give me some map which is linear. X, y going to, what about x plus y? Is this linear?
Yes, sir.
Yes, right? Can you modify the right hand side, still get linear? So of x plus y, you have the plus, but modify these two. What about this?
Linear.
A and B are fixed real number, okay? X comma y going to ax plus by. This is linear, right? For any pair A and B, or if you want to say that AB is in R2. Fix an AB in R2, then x comma y going to ax plus by is a linear map. What is, can you give me the values of A and B in terms of this map? If you call this T again, what is the value of A? It is image of which point?
1 0.
A is T of for
T of
what
one.
values of x and y do you get A on the right hand side? T of, you want to get A here, so you take x equal to 1, y equal to 0, right? T of 1 0. And similarly B is T of 0 1. Okay. What do you know about these two vectors 1 0 and 0 1? E1
Yes.
is 1 0, E2 is 0 1. So these form a basis for R2, isn't it? So A and B are just the images of these two vectors under this given linear map. And although we don't need it at the moment, but what is the right hand side? Right hand side is something familiar to you. Ax plus by is AB dot xy, right? This dot product, in R2. AB dot xy is AX plus BY. This is the usual dot product, or if you want AI plus BJ dot XI plus YJ is this AX plus BY. So with respect to the usual dot product on R2, what have you done here? Fix a vector AB in R2, take the dot product of any vector with that fixed vector, you get a linear map from R2 to R. By the way, of course, these are, what are such maps called? Linear maps into the base field. They are called linear functionals, right? And of course, now you know what are all the linear maps from R2 to R. All linear maps are of this type. So linear maps from R2 to R are all of the form TAB. Yeah, so this map I am calling TAB. AB is a fixed vector in R2. So every linear map from R2 to R is of the form TAB for some AB in R2. So TAB is defined, T of AB at XY is AX plus BY. All right? And why do you want to talk about linear maps? When you want to study calculus, you have all seen what partial derivatives are. Have you? Suppose you have a function of two variables, let us say. Of xy. F is from R2 to R, it's a real valued function on R2, let us say. Of course, you can have some open domain on R2, but real valued function. So how is the partial derivative defined? What is the definition? You have seen partial derivatives, right? Okay, let us start with one variable itself before we go to two variables. So how is the derivative defined? F from R to R, or some interval from R to R. What is the definition of the derivative? So this is limit of something right? Provided the limit exists. So if the limit exists, so where does this belong to? What is this? Is this a number? Is it a map? What is it? What is the right hand side? F is real valued function. So this is a real number. This is a real number. This is a real number. So the whole thing here is a real number. Okay, so we're taking limits in the space of real numbers. So we're going to end up with a real number again. Okay. What happens if you replace the right hand side when does this right-hand side make sense? Suppose, for example, you have a function from R to R2. Does this still make sense? Forget the limit for the moment, but what will this be? What is this meaning now? F takes values in R2. So what are these things? These are points in R2. F of x plus h is an element of R2. F of x is an element of R2. So what is meant by this minus here? Of course, you can add and subtract elements in R2. R2, after all, is a vector space, right? xy plus uv is x plus u, y plus v, right? That's how we add. You add coordinate wise, add the coordinates, respective coordinates. And of course, a times xy is ax comma ay. So that's how R2 becomes a vector space over R. So plus or minus here is a vector space addition. xy minus uv is x minus u, y minus v. So the numerator here is in R2. What about this h? H is in R. So what is the meaning of this? So by definition, this is 1 over h times f of x plus h minus f of x. So this is a vector in R2. This is a scalar. So this is a scalar multiplication. So this whole thing, therefore, is in R2. So we are multiplying the scalar 1 over h, the vector f of x plus h minus f of x. Okay? And limit in R2 makes sense. Okay? R2, how do you take limits in R2? You have the usual metric, right? So now the limit on the right hand side is the limit in R2. So just as you talked about differentiability of a real valued function on R or an interval on R, you can also talk of differentiability of functions on R taking values in R2. So f prime x is limit of f of x plus h minus f of x 1 over h times this vector as h tends to 0. So everything makes sense, whether it is R or R2 or even Rn for that matter. So the right hand side is the scalar multiple of the numerator, which is a vector. So when you take the limit, what will you end up with? You will end up again with something in R2. So if you're starting with real valued functions, this is going to be a real valued real number. Okay? But if you are looking at a function taking values in R2, you are going to end up with a point in R2. So f dash x, therefore, in this case, if the limit exists, this is going to be a point in R2. More generally, if you are taking functions with values on Rn, you are going to end up with a point in Rn. So differentiability makes sense for any function f defined on R or on interval. Instead of R, of course, you can take any interval AB if you want. It doesn't matter. Or any open set in R. But now taking values in R2, for example, or Rn in general, it may be R or R2, R3, anything on the right hand side. Values in some Rn. So you can still talk of the derivative at a point in R2 or Rn. Okay, so let's get back to one variable itself, real valued functions themselves. F is from R to R. Differentiable, let us say. F dash x is a real number for any x. Now, if you go back to the question, the first question that we asked, all the linear maps from R to R, okay? We have seen that any linear map from R to R is of the form k times x, t of x equal to k times x. So every linear map from R to R is of the form tkx equal to k times x for some fixed real number k. So that way we said we can identify set of real numbers with the set of linear maps from R to R. The space of linear maps from R to R can be identified with this space R itself. So if you make that identification, if you call this as k, this you are starting with a differentiable function, you are looking at the derivative of the point of the function at a point x, if you want to call it kx. So the number kx can be identified with so instead of thinking of this as a real number, you look at think of this as multiplication by that real number f dash x. So at any point t, this is f dash x times t. Similarly, if you look at functions from R to R2, we again determine all the linear maps from R to R2, right? All linear maps from R to R2 are of the form t sub a comma b. Okay? Fix a vector AB in R2, just take the scalar multiple of that. That gives the linear maps. So if you are having a function from R to R2, which is differentiable and so on, and let us call it t, real number t now, instead of calling it as x. F dash t is an element of R2, call it a comma b. So think of a comma b as the linear map TAB that we looked at earlier. What is TAB? TAB of t is this t times a comma b, or ta comma tb. why do you have to do this? What is the advantage in doing this, at least? So now let me get back to the question I asked again earlier about the partial derivatives. You have to tell me what partial derivatives are for us to go ahead. Suppose f is a real valued function on R2. What is meant by the partial derivative of the function with respect to, say, x, for example? What is the meaning of this? How do you define this? Only if you tell me what this means, we can go ahead and see why we have to look at linear maps. All of you have seen partial derivatives, right? So unless I get some response to this, I cannot go ahead.
Hello.
Yes?
Limited delta y tends to 0 f of x plus delta
Huh?
x. Definition of dou f by dou x.
Yeah. Limit?
Delta y tends to 0.
Something tends to 0. Okay, let me call it h. H tends to 0 of
F of x plus h. Y y plus h minus f of x y divided by x. H.
Yeah, so provided the limit exists. Okay. What is this? X plus h comma y. This is xy plus h times something. What is that something?
1 0.
1 0. Okay. So if you call this point as point xy as p, this is p plus h times e1. Okay, with our earlier notation, this is the usual basis vector e1. So similarly, if you look at the other partial derivatives, you have to look at f of p plus, in place of e1, you will get e2, right? Limit of this. So these e1 and e2, what are these? These are the usual basis vectors. Okay, 1 0. This is e1. This is e2. Now suppose I take any vector v instead of e1 or e2. Then what is this? So you look at f of p plus h v minus fp over h. So what are you doing? See, when you have, so P is some point, okay, earlier, so P is this. So what you are doing is P plus, so E1 is this. So H times E1 is something like this, small h. So this is H times E1. So this is P, this is H times E1. So this vector there. Rather, let me draw it separately, okay? So P vector is like this, H times E1 is like this. So you have to add, so you take the, so this is HE1, this is P. So this is P plus HE1. Now you take any vector P, don't, instead of E1, take a E1 or E2 for that matter, you take any vector V and do the same thing. So what you are going to do is, you are looking at P there and V, so this is H times V, so we're going to get something of form like this. So this vector there. So if this limit exists, what is it called? You have seen this? If this exists, it's called a directional derivative of f at P in the direction of V. Of course, if V is 0, then you get nothing, right? You get numerator is 0, you are going to get 0 only. So V is not 0, it gives you direction, the direction of V, okay? So the directional derivative. So we can call it something like this. So dpf, no, what is it called? Which is better? Derivative p dfp at, let us say. So the directional derivative of f, the direction of p. For every vector v, okay, you get what? A real number, okay? So this is, we are looking at functions on R2, but taking real values. So this is dfp. So this is a real number, if it exists, okay? So for every vector, so what do you get? If you look at this dfp, then we going to dfp at v. So this is a map from R2 to R. Okay? But what kind of map is this? And check that this map is linear. Okay, so what I'm saying now, therefore, is if you have a real valued functions on R2 at any fixed point P, taking the directional derivatives give you a linear map. Okay, taking the directional derivatives in all possible directions gives you a linear map from R2 to R. So we'll come back to this next time. So we'll stop here now. We'll try to check that this map is actually linear. So we will know why we should consider linear maps. So we'll take it up from here next time. But in the meantime, we'll try to check that check the linearity of this map. Okay. So we'll stop now.